Now we are continuing with module 6, hierarchical clustering algorithm, which is called BIRCH algorithm. BIRCH algorithm is a balanced, iterative, reducing and clustering using hierarchies. So it is there are multiple phases in this particular clustering, and it is an hierarchical clustering which uses a clustering feature tree. But before I start with BIRCH, I need to refresh your memory on B plus trees. So let's look at B plus trees just to remember what is B plus trees. Now if you remember, we did B trees and B plus trees in data structures. You should have done it, or I remember that we did it in database. When we did PDD, we had done B plus trees too. Now B plus trees is very simple. Just like B trees, it is a height balanced tree. B plus trees are height balanced trees. In the balanced tree over here in this, but this I have drawn the end. The numbers that we are going to use to create the B plus tree is 1, 4, 7, 10, 17, 21, 31, 25, 19, 28 and 41. We have 11 numbers. Now I'm going to draw a 4-way B plus tree. That means there are only at any particular stage the maximum number of children nodes for a particular node is 4, and because it is a B plus tree, values will only be in the leaf node. You can see that all the 11 values will be available in the leaf node. Each of the leaf node will represent a cluster. Later on when we use it for BIRCH, I will tell you how it represents a cluster. Now let's begin. To begin with, we already know that each node can have only 4 children nodes. This is how it is. Each node can have only 4 children nodes, and the index of each, whatever number is over here, numbers, you remember that B plus tree and B trees are a variation on binary search trees. So the same rules follow. Whatever number is there in the particular node, all the numbers less than that particular value will be to the left side of the tree, of the node, and to the right side you will have numbers greater than this particular tree. Now the first 4 numbers will simply be stored in the ascending order 1, 4 and 7. Now our problem begins when we want to store the next number 10. I want to store the next number 10, but it is not possible to store the next number 10 in the root node itself. So I have to split this. Okay, now when I split this, I can split it. I've got 4 numbers over here. If I had 5 numbers, I would simply take the middle element and put it in the root node as the index, and I would continue. But since I have got 4 numbers, I have to choose either the left balanced tree or left biased tree or right biased tree. Now if I am using the right biased tree, then 7 will be the number that will go in the root. So this will now become, I have got the root with only 3 elements possible. 7 is the element which I am taking up, and to the left of 7 I have got 1, 4, and because this also will have one more element, there is space for one more element. Okay, and to the right of 7 I have got, first of all I should have the value 7 also, and then the new element which was supposed to be placed in the previous element. So now I have got 7 and 10 over here. So let's look at 17. Where should 17 go? 17 should go to the right of 7, and I have space over here, so I can simply put the element 17 over here. Then I have got the element 21. Where should 21 go? 21 is supposed to go to the right of 17, but I do not have space over there. But I do not need to split, I need to, now if I have 21 over here, I need to again split this. So what is going to happen? This will, now I have got over here 7. The value 17 is the number which is going to be pulled up. So I will have 17 over here, and to the right of 17 I will have 17 and 21, and there's one more space left. To the left of 17, I've already got 7 and 10. So I will have 7, 10 and 1 space left. And over here, we've not made any changes over here. So we will have 1, 4 and 1 space left. So now we are going to continue. The next number is 31. 31 can be placed, it's supposed to be placed to the right of 17, and over here I've already got 2 elements. I have got space for 31, so I'm placing it over here. Next, I have got 25. Now what do I do with 25? 7, it is greater than 17, so I have to come here. But I do not have place over here for 17, for 25. So it is actually supposed to be placed in between 21 and 31. Okay, and since I am using the right bias, I am going to push this element on top, and this will split at this particular point. It will get split at this particular point. So now I will have 7, 17, 25. To the left I have no change here, 1, 4 and there is a space. Over here also no change, 7, 10 and I have got space. Now to the left of 25 I have 17 and 21 and 1 space. To the right of 25 I have 25 and 31 and 1 space. So now I'm filling the available space before I try to split. Only if I do not have place in the leaf as well as in the parent nodes, then I will do a split. So now next I have 19. Now again I have to place 19 after 17 and before 25. So I am supposed to place it over here. I will simply remove this 21 from here, put it over here, and this will become 19. So 19 is placed. What about 28? 28 can be placed over here. I simply put 31 over here and 28 over here. Now 42. I have a problem. 42 is greater than 25. This is completely full. So I need to place 42 over here. So again I need to split. Now my problem is when I try to place this on top over here, I need to place 31 over here. When I try to place it over here, my problem is there is no place over here also. So now I have to create a new root node. So this element will go up into the root and there will be a split from this direction. So now it is going to be in this way. We will have root node. In the root node I have 25 and 2 spaces. To the left of 25 I have, as we have over here, to the left of 25 I have got this elements 7 and 17. So to the, sorry, I am not going to, I'm splitting this 7 and 17. So on this side I will have 7, 17 and a space. To the right, now since this is not a leaf node, I will not write the index value again over here. Instead, I will simply write the number that is greater than 25. So in this particular case, I have, after 25 I have 31. So I don't want the index again. So I am simply going to write 31 over here. Okay. So now what are the elements that we have to the left of 31? I have this element 25 and 2 spaces. Do I have an element to the right of 31? Yes. I have to the right of 31, I have got the elements. I have to write 31 because this element is there over here. So I am writing 31 and 42. Okay. Now after this I have all these elements. There are no changes over here. So just as previously, before the 7 we have 1, 4 and there is a space. After 7 we have 7 and 10. To the right of 17 we have 17, 19 and 21. Now if you look, all the elements that we have, there are 11 elements over here. All 11 are placed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where I have missed something. What have I missed? 19, 21. Sorry, here. 25, 28, 25, 28 and 31. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All 11 elements are placed. This is how a B plus tree works. Now in BIRCH algorithm, we'll be using the concept of B plus tree to execute the algorithm. So please remember this, you cannot afford to forget this. Now let's continue with BIRCH algorithm. Now in BIRCH algorithm, you can see, I already told you that it is a multi-phase hierarchical clustering. So we are going to build a tree, and we are going to build the tree using B plus concepts. The biggest advantage of the BIRCH algorithm over our agglomerative or our divisive method is, one, both the agglomerative method and the divisive method works on comparatively small amounts of data. But in data mining, all of our data is normally very large. So we require scalability, and BIRCH algorithm allows for scalability. The second thing is that I told you earlier that when we are using agglomerative or divisive method, once we make a split decision or a merge decision, we cannot go back, we cannot undo the decision. But this method allows us to revisit our decisions once again and make any corrections. So it solves the problem of scalability and inability to undo previous steps. Now the thing that we are going to do is, we are not using the data itself for our creation of our tree. Instead, we are using cluster features. To summarize a cluster, a number of data, first step of BIRCH is doing a rough clustering. After doing a rough clustering, we summarize the data of each cluster and then use that summary values to create the proper clustering. Okay, so each time we create a cluster feature tree, we are not actually using data, we are using the features of a cluster to create the tree. And this achieves speed and scalability with large amounts of data, and it is incremental clustering. I don't have to do everything from the beginning every time a new data appears. Whenever new data appears, I simply push it into whichever cluster it belongs to at that particular time, then recalculate the centroids and readjust whatever data needs to be readjusted. That's the only thing that I do. So it allows for speed, scalability and incremental clustering. Now we're going to look at how a cluster feature, this is important, please pay attention. Okay, how a cluster feature is created. A cluster feature is a 3-element vector. We have got 3 elements in the cluster feature. Okay, now look at this. We are taking an example. Supposing that I have a cluster C1 with 3 points, 2, 5, 3, 2, 4, 3. Then cluster feature is a vector with the first element n, second element ls and the third element ss. Now n is the number of clusters. So here we have only 3 points, sorry, number of points. So here we have only 3 points, so n is 3. ls is the sum of the coordinates of the point. So all the x coordinates will be added. So we get what? 2 plus 3 plus 4. 2 plus 3 plus 4 is 9, comma, y elements 5 plus 2 plus 3, that is 10. So ls is 9, 10. It is simply the sum of the corresponding coordinates of all the points in that particular cluster. Here we have the square sum. So find the square of 2, 4, square of 3, 9, square of 4, 16. So 4 plus 9 plus 16 is equal to 29. Similarly, 25 plus 4 plus 9 is equal to 38. So here we have square of the sum. Now this CF1 will represent cluster C1. And what are the things that we can calculate from this particular value? Simple. For this particular set of numbers, the centroid can be calculated as LS divided by N. So LS is over here and N is over here. So I get LS divided by N means 9 divided by 3, 3, and 10 divided by 3, 3.3. So my centroid is, for this particular cluster, is 3, 3.33. Similarly, I can find the radius of the cluster and diameter of the cluster. So every time a new element is put into a particular cluster, we will be calculating the radius or the diameter. And there is a threshold maintained for both radius and diameter. That means how big a particular cluster can be. How large the radius is or how large the diameter is already prefixed. Based on that, I can decide whether a new number should go in a present cluster or whether I should divide the cluster again into 2. So do you understand how the B plus tree works? In B plus tree, we are simply using the number. Here we are not using the number only, we will be using the values of the radius and the diameter. These thresholds will also be used to decide whether a cluster must be kept as a single cluster or whether the cluster must be divided. Okay, now calculating R and D, see, look at this formula. It is calculated from SS, LS and N. So if we have stored the values of N, LS and SS, we can calculate the radius of the cluster and we can calculate the diameter of the cluster. Now, because I am drawing the tree structure, okay, if I have got two clusters CF1 and CF2 and these two are leaf nodes, then the parent node will be represented by CF1 plus CF2. So N1 plus N2, LS1 plus LS2, SS1 plus SS2 will be the element. That means if I've got two clusters and I know the N, LS and SS value of those two clusters, then combining those two clusters will simply be add the N values of CF1 and CF2, that is N1 plus N2, and add the LS1 values of CF1 and CS2, that is LS1 plus LS2, and add the SS1 values of CF1 and CS2. So SS1 and SS2. So the combined cluster will have this as N value, this as LS value and this as SS value. CFs are additive. Okay. Now we are going to go into a little bit more details. Now remember that building the CF tree is similar to the B plus tree. A height balanced tree, but what does it store? It does not store the data points. Instead, it stores the cluster features for a hierarchical cluster. The non-leaf nodes stores sums of the CFs of their children. So, if I have a non-leaf node, not the leaf, but the non-leaf node, like over here, okay. Now, this is a non-leaf node. This is root, of course, but this is a non-leaf node. Now, to find this value, CF1 will be equal to CF1 plus CF2 plus etc. CF1K. Do you get that? So, just sum all these values, that is the value that is stored over here. In this level, whatever is down over here, all those will be added to get this particular value. This is how the data is stored. Now, a CF tree has two parameters. This is important. Based on this, we decide, not based on the values of LS or SS or N. Based on the branching factor and the threshold T, we will decide whether a cluster is supposed to be divided or it can remain as 1. Okay. Now, what is B? B is simply the number of non-leaf nodes, number of children nodes in a cluster. Maximum number of clusters per non-leaf node. The maximum number of children that a non-leaf node can have. This is similar to what we have in B plus tree. But there is another thing. Over there we did the branching based on the value of the numbers. Here we are going to do the branching based on this threshold. Now the threshold can be the radius or the diameter of the cluster. Now a maximum diameter of children clusters are defined. If any time we find that a child cluster is becoming bigger than this particular diameter that is specified, we choose that time to divide the cluster and we pull up the element tree upward. This is how we build the CF tree. Just this is where the B plus tree concept is used. Now, actual BIRCH algorithm. First, using B plus tree concept, you build the CF tree. Once the CF tree is built, you already have a clustering. Okay. Now, each time when we do the clustering, I told you we are not storing the elements as such. Instead, we are going to store N, LS and SS. Every time a new element is added, we change the value of N, LS and SS till T is, the threshold has become violated. When threshold becomes violated, we split the cluster. That's what's happening over here. And we have first a clustering. We have a clustering. After this clustering, we use from this N, LS and SS, we can calculate the centroid. So, using LS divided by N. Here's how we calculate the centroid. X naught is equal to LS divided by N. So now, when we did the first part, we got a number of clusters. Find the centroids of each of these clusters. And in the second step, no need to use all the data elements in the database. Instead, use only these centroids. And once again, do the clustering based on centroids only. Once that is finalized, there is no changes in the centroid values. Once there are no changes in the centroid values and the tree remains the same without any changes, then we use any particular clustering method. Now you can use agglomerative method or you can use divisive method. Use any method that you want and then do the clustering on the leaf nodes of the CF tree. So we are doing clustering only for the centroids. This is our second scan of the data. Once the centroids are fixed, go through the elements once more and check that your centroid values are the same. This is your BIRCH algorithm. We do not need to do an application for BIRCH algorithm, but it is a simple case. You can try it out with our previous example. That is the example which we used for medoid, K-medoid algorithm and K-means algorithm. You can use that and try it out if you want. It will take some time, but it is quite simple. You can do it. Each time you are going to use not the values itself, but N, LS and SS. I will take a photo of that particular algorithm with BIRCH and I will put it in the next class. Now, this is how the tree will look like after it has been created. Now this is effectiveness of BIRCH. First of all, I told you that the time complexity will always be order of n because the database is going to be scanned only once. It's not going to be scanned again and again. Next, it is linear scalable. That means linear scalable means incremental. You just have to add the extra data whatever is coming to the existing CF tree. You do not have to go through all the data again. Okay, so you not only that, the quality of clustering is good compared to other methods. The problem is that since each node in the CF tree has a limited number of entries due to its size, it may not correspond to a natural clustering because we are fixing the diameter. Maybe the natural clustering, the diameter is not what we have fixed as T. Okay, so it may give you a skewed clustering, but the assumption is that we get good quality clustering because we fix T based on domain knowledge. If the clusters are not spherical in shape, that is, if distance measure is not a good measure, then in that case, BIRCH algorithm may not perform properly because our BIRCH algorithm is also based on radius and diameter. This is the effectiveness of it. Has got many good qualities, but there is problems in this also, and that leads us to our next density based algorithms. That will be in the next class. Thank you.